This topic is about pH, and pH is involved in everything imaginable with biology and chemistry and material science. pH is important in making packages, inside of the fruits and vegetables we eat, in the canning and everything else. So you probably have heard of pH, but we're going to talk about what it really is, at least in a simplistic point of view, and why it's important with some specific examples that I'll use for product processing and cooling, and things we can do to monitor and adjust the pH along the way. So first, let's go back to an atom. We all know, I hope we all know, that everything solid, liquid, and gas, all matter, is made of atoms. Atoms are a combination of three building blocks: the protons, positively charged particles; electrons, negatively charged particles; and neutrons. They have no charge. And the simplest of all atoms is a hydrogen atom, a single positively charged proton orbited by a single negatively charged electron. Now, it's very unstable in this configuration, so we don't find single hydrogen atoms all by themselves. We find H2, two of them together, or maybe H2O, which is two hydrogen atoms mixed with one oxygen atom, and that makes water. But this is the basic fundamental components of a hydrogen atom, even though it doesn't exist in this form, at least not for very long, in nature. It'd be very, very, very unstable and reactive with other things. Something else that we should all be familiar with is carbon. We are carbon-based life forms here on Earth. And as far as we know, all life is carbon-based, but it doesn't necessarily have to be. I'll leave that to you science fiction fans and future scientists looking for exobiology. Anyway, what is a carbon atom? It contains 6 protons, 6 neutrons, and 6 electrons. It's also highly reactive, but not in the same explosive sense. It is reactive biologically to make all kinds of complex things like people, like bacterial cells, like proteins and carbohydrates and gasoline, and so many different things are based on carbon. So that's the structure of an atom. Now, I did mention 2 hydrogens and 1 oxygen is H2O. And this little stick figure diagram on the side shows what a hydrogen atom might look like. It does have an angular arrangement between the 2 hydrogen atoms as they join or covalently bond with the water atom to make the oxygen atom. We say that again. The 2 hydrogen atoms have a specific angle where they covalently bond to the oxygen atom to make a water molecule. I'm not going to worry about covalent bonding in this class, but it is the way atoms come together to form many of the substances we're familiar with. They bond by sharing electrons, and that's called a covalent bond. And so here you have water. It's not HOH in a straight line. It's at an angle. And this makes a huge difference, because think about it, what we just saw with the previous one. This is carbon, not oxygen. Oxygen is actually bigger. Oxygen is number 8 on the periodic table. So it has 8 protons, 8 positive charges. So if I look at this, there's 8 protons here, 1 proton here, and 1 proton here. 8 positive charges in the oxygen, 1 positive charge in each of the hydrogens for a total of 10 protons. In addition, there is 10 electrons to balance this out, 10 negative charges orbiting this whole structure, this water molecule. 10 of them are rapidly zipping around in very specific patterns. I won't get into orbitals and how the orbiting works, but it's quite interesting how these 10 electrons orbit and hold the water molecule together with their charges. Now, where are those electrons attracted most strongly? They're attracted to the oxygen end. It's 8 positive charges. So the electrons, as they're orbiting at a phenomenal rate of speed around this thing, they're going to hang out a little bit longer over on the oxygen side because of that extra pull of these 8 protons and a much less pull from single protons in the hydrogens. So what does that mean? That means that water is going to be slightly polar. Since the electrons hang out near the oxygen a little bit more, their negative charge is going to be a little bit more on the oxygen end. It's going to be a little bit more negatives than the 8 positives. And there's going to be a little less electron activity over here on average, kind of exposing these protons a little bit and their charge. So you end up with what's called a partial positive charge on the hydrogen end and a partial negative charge on the oxygen end. That makes water polar. And that's why water sticks together like magnets in a way. At the molecular level, it's almost like little molecular magnets sticking to each other. Please don't say that to a chemistry teacher. They'll groan and do the face palm or something, because it's not magnetism. It's not magnetism at all. It's electrical charges. It's these charged particles. And these charges cause this hydrogen bonding, where the hydrogens that are slightly exposed for their positive charge are attracted to the next water molecule nearer to it, and they're attracted to the oxygen end because that's the negative charge. Positive hydrogen end attracted to the negative oxygen end because of the excess of electrons hanging out there. All right. So that's a water molecule, and that's why water behaves the way it does. And I'm not going to get into any more of that in this class. In my soil science and plant science, we go off on polarity of water and how that affects all kinds of things. In here, I'm not too worried about going any deeper into that. But as stable as water is, it's not perfect. It does ionize or come apart. And when it comes apart in a very specific way. It has one of the oxygen or one of the hydrogens going away with the oxygen and stealing an extra electron. The electron is much more stable going with the hydroxide ion, the OH. And it's called an ion because it has more or less electrons and it carries a charge. In this case, it has more electrons. All 10 electrons go with this OH. There's 8 positive charges with the oxygen, 1 positive charge with the hydrogen. That's 9 positive charges, but it takes all 10 of the electrons. There's an extra electron, making this a negative ion, negatively charged ion, otherwise known as an anion. Anion are negatively charged ions. On the other side, we get the positively charged hydrogen with a single positive charge. Now, it lost its electron, so what's left? A hydrogen ion is nothing more than a free proton, an escaped proton. That's it. The proton escapes. And that happens all over the place in biology. We have things in our digestive system called proton pumps. Maybe that's why you have protease inhibitors, things to stop acid reflux and a sour stomach. They're because we pump these hydrogen ions, we create them to acidify our digestive tract inside our stomachs. But it's happening in plants and photosynthesis. It's happening if you're drinking a glass of water right now, it's happening in that glass of water as you sit there. Many trillions upon trillions upon trillions of water molecules, some of them spontaneously ionize, creating hydroxide and hydrogen. It just happens. But it's not just water that can do this. Many substances have the ability to ionize, and in the process of ionizing, becoming an ion or a pair of ions, they can generate either hydrogen ions or hydroxide ions. And we call these things acids and bases. These substances that can ionize, creating excess hydrogens or excess hydroxides. If it ionizes to create more hydrogens, we call it an acid. If it ionizes to create an excess of hydroxides, we call it a base. So what is pH actually? pH is called potential hydrogen. More specifically, it's the hydrogen ions we're talking about. What is the acid potential of these hydrogen ions based on the ionization of materials in that liquid solution? We're always talking about a water solution when we're talking about pH. Now, it could be in your blood, in your cells, in the river, lake, stream, rain clouds. pH is something that's based on liquid water environments. And we measure that hydrogen ion activity, the acid forming activity in a water solution. That includes fruits, vegetables, and all of their processed products. pH is really important in these products. So let's look at another way to express pH. pH is a convenient way to express the hydrogen ion concentration of a solution based on this simple mathematical equation. The pH, or the potential hydrogen, is equal to the negative log base 10 of the hydrogen ion concentration. What the heck does that mean? Well, whenever you have square brackets, that means the concentration of in chemical equations. So the concentration of hydrogen ions, or the concentration of protons. The negative log base 10 means something that increases or decreases exponentially by a power of 10. What is an exponential increase or decrease? Well, 1, 10, 100, 1,000, 10,000, 100,000, a million, etc. I'm just adding a zero every time. I'm multiplying by 10. And there are lots of things in biology and other sciences that are easier to represent as a logarithm rather than a straight line. And in physical sciences, one thing in California we're familiar with is the Richter scale. Well, a magnitude 2 earthquake is actually 10 times as powerful as a magnitude 1. A magnitude 3 earthquake is 10 times a magnitude 2 or 100 times a magnitude 1. A magnitude 4 earthquake is 10 times a 3, 100 times a 2, and 1,000 times a 1. And we know these as 1, 2, 3, 4. And that's just daily rock and roll in California. 1, 2s, 3s, and 4s. When you start hitting 5, 6, that's an earthquake. That's not just the little bit of shake and shimmy. That's a real earthquake. And you're adding another 0 at 5, another 0 still at 6. And so they get really big really fast. And pH is the same thing. When you're talking about the hydrogen ion concentration, when the pH number goes up, the hydrogen ion concentration actually goes down. And that's why we call it the negative log, because it's in the opposite direction. It's a fraction, which you'll see momentarily. So the pH scale is logarithmic, as I just mentioned. A difference of 1 unit in pH represents a 10-fold change in the hydrogen ion concentration or the proton concentration in a water solution. So here you can see the pH scale represented with the lowest pH at the top. Pure hydrochloric acid is a pH of 0. What does 0 mean? It literally is the exponent, 10 to the 0 power. And ask your math teacher or something, but any number to the 0 power equals 1. So this is just 1, a pure concentration, the highest you can get in a water solution. It doesn't mean you have a handful of pure hydrogen ions. You can only have so many hydrogen ions in a water solution. You need water there, right? And in a hydrochloric acid solution, you also have some chloride ions. You have to have some of those too. So it's not pure. 1 is just the highest concentration, or excuse me, 0 is the highest concentration you can get. Then 10 to the negative 1, again, in math terms, it's a fraction, 1/10. 10 to the negative 2, 1/100. 10 to the negative 3, 1/1000. 10 to the negative 14, what is that? I think 10 trillionth? 1/10 trillion? That's a really low concentration of hydrogen ions. And what do we have at that extreme low hydrogen ion concentration? A pure solution of sodium hydroxide in water. Hydrogen ions just don't exist there. If a hydrogen ion tries to exist there, it immediately is turned into water. 1/10 trillion, the concentration of hydrochloric acid. And at the extremes, bad things happen. Hydrochloric acid, extremely strong acid that in its pure state is deadly. But we have hydrochloric acid in our stomachs. That's how we digest our food. But we don't digest our food at pH 0. That would kill us. We digest our food at pH 2, a diluted hydrochloric acid where our stomach lining can handle it. What else is in that general range? Lemon juice is very acidic. A little less acidic, a little higher number, around 3 or so. You have vinegar, cola, beer, 3 point something, maybe up to 4. Tomatoes are 4, 4.4, 4.5. Coffee, normal rainwater. Rainwater, isn't rainwater like pure and neutral? No, rainwater is actually a little bit acidic. Natural water, not because of acid rain, natural water in Earth's environment before humans ever had anything to do with it has a little bit of acidity. It's a little bit acidic. So anything under pH 7, all the way up through urine and saliva that is just slightly acidic, is considered an acidic solution. At or right near 7, is considered neutral, where you have a balance between the hydroxide ions and the hydrogen ions. They balance each other out. You're at neutral pH. And so pure water, which isn't water in nature, but water that's been made pure through laboratory purification, human interaction. Blood is right there, just barely off of 7. And you don't want your blood going very far away from pH 7. That'll kill you. And then on the other side, above 7, at the bottom of this chart, but numbers that are higher than 7 include the basic things, the basic substances, otherwise known as alkaline. Now in soils, I get a little cautious about the use of the word alkaline because there's a very similar sounding word, alkalinity, which refers to something related, but not exactly the same. So I prefer the use of the term basic. Then you don't get confused between alkaline and alkalinity. But seawater is slightly alkaline. Baking soda, more alkaline, more basic. Very, very salty waters like the Great Salt Lake, more basic. Milk of magnesia, something you would take for a sour stomach, is an acid countering material that's safe to drink. So you drink a few tablespoons of milk of magnesia and it can settle your stomach. Household ammonia, don't drink that. It will neutralize the acid and neutralize you in the process. Bleach, etc. You get the idea. So let's take a quick break.